Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering. Welcome to the overview of VLSI manufacturing technology. In this video, we'll walk through the essential infrastructure and fabrication processes involved in semiconductor device fabrication. We will review ultra-clean room environments, silicon wafer growth, layout to mass generation, and several key processing steps involved. Hope overview of this complex subject helps in appreciating the processes involved in creation of semiconductor devices. So, let's get started. VLSI fabrication starts with high-purity single-crystal silicon grown using the Czochralski process. The silicon ingot is sliced into thin wafers and polished to a mirror finish. Using physical layout GDS2 layout data, photomasks are generated. Clean silicon wafers undergo fabrication process in ultra-clean rooms. Using photoresist polymer and different masks in photolithography process, sequentially several material layers are created over silicon substrate. Components interconnectivity is established with aluminum or copper interconnects. Chemical and mechanical planarization process creates flatness of created layer surfaces. Tested wafers are then scribed, mounted, bonded and encapsulated to form a finished device. Final finished device electrical testing is carried out to ensure conformance to datasheet parameters. Periodically, statistical sampling batch acceptance for quality assurance, environmental and reliability tests are carried out to meet different customers like commercial, industrial and defense specifications. Silicon single crystals are grown using the Czochralski method, in which a seed crystal is slowly pulled from molten silicon to form a cylindrical ingot. The ingot's diameter typically ranges between 100 mm to 300 mm, with crystal orientation like 100 or 111. Doping is introduced during growth: boron for p-type or phosphorus/arsenic for n-type, to control resistivity between 0.01 to 1000 ohm centimeters. The ingot is then sliced into thin wafers using diamond wire saws, with thickness around 725 mm for 300 mm wafers. Rounding and grinding follow to improve mechanical strength and flatness. Initial cleaning removes slurry and particulates from slicing. A brief dip in hydrofluoric acid eliminates native oxide. Final rinsing with DI water ensures surface purity. Wafers are then dried and inspected for defects. This process yields high-quality substrates for VLSI fabrication. Following are some of the clean room features employed in the semiconductor device manufacturing environment. For ensuring the process stability, clean room temperature is tightly regulated between 20 to 22 degrees Celsius. To prevent static charge buildup that leads to material degradation, the humidity is maintained at 40 to 50% RH. Airborne particles present in the processing environment can bridge the interconnect, block deposition or etching, or distort the photomask image transfer. This phenomenon is controlled by filtering predefined size particles. Example: a class 100 cleanroom allows only 100 particles of less than or equal to 0.5 micrometers size particles per cubic meter. Static electrical charge damage is prevented by employing features like specialized flooring, protective operator garments and tools, robos for material movement, etc. A high-efficiency particulate air filtering system is employed, that filters 99.97% of particles of greater than or equal to 0.3 micrometers, and thereby ensures ultra-clean air. Once a circuit is completely designed and verified at the layout level, it is stored in the industry-standard GDS2 format. This file contains the geometric representation of all layers required to fabricate the chip. The mask extraction process begins by mapping each layer of the GDS2 layout to the corresponding layer of the semiconductor process, such as diffusion, polysilicon, contact, or metal. EDA tools interpret the GDS2 data and generate individual mask patterns for every process layer. These masks act like stencils that define where material will be deposited, etched, or doped on the silicon wafer. During extraction, design rule checks, DRC, and layout versus schematic, LVS, verification are performed to ensure that the generated mask data matches both the physical constraints and the intended circuit function. Finally, the verified mask data is converted into a format suitable for photomask fabrication, where high-resolution mask plates are using electron beam or laser writers. These photomasks are then used step by step in the lithography process during wafer fabrication. The table shown presents processes, processing equipment, and function of each processing step. Following are the sequence of steps followed in creating mask pattern layers on the substrate. Photolithography in VLSI begins with wafer cleaning to remove contaminants. A photoresist layer is spin-coated onto the wafer. A soft baking follows to evaporate solvents and stabilize the resist. The wafer is then aligned with a photomask containing the desired pattern. Ultraviolet light exposure transfers the pattern onto the photoresist. The wafer is developed to dissolve exposed or unexposed resist areas. Etching transfers the revealed pattern into the underlying layer. Remaining photoresist is stripped off after etching. This process is repeated for different material layers of the VLSI structure. After photolithography and etching steps, residual photoresist must be completely removed to prevent contamination and ensure clean surfaces for subsequent processing. Photoresist, when exposed to plasma, it gets physically and chemically degraded. When wafers coated with photoresist are loaded into the chamber, the plasma reacts with the carbon-based photoresist material. Plasma is full of tiny reactive particles that break down the photoresist, which leads to carbonization or hardening of the resist. These residues are often referred to as pulverized and they lose solubility, making wet stripping ineffective. In an asher, when photoresist is exposed to plasma, it gets pulverized and turns it into harmless gases, which are safely removed from the chamber. Photoresist loses cohesive film structure and become difficult to remove by conventional solvent-based methods. The asher does this gently, without damaging the wafer and creates a stable surface for the next processing step. The epitaxial reactor system is designed to deposit a high-quality crystalline silicon layer onto a silicon wafer. The process typically uses chemical vapor deposition, or CVD, inside a high-temperature reactor chamber. Reactive gases like silane or trichlorosilane, carried by hydrogen, into the chamber. The wafers are heated to temperatures around 1000 to 1200 degrees Celsius. At these temperatures, the gas molecules decompose, and silicon atoms begin to deposit on the wafer surface. The deposited atoms align themselves with the crystal structure of the underlying substrate and is called epitaxial growth. There are two types, homoepitaxy, where silicon is grown on silicon, and heteroepitaxy, where a different material is grown on silicon, like gallium arsenide. The growth mechanism involves three main steps: adsorption of reactive species onto the wafer surface, migration of these atoms to energetically favorable lattice sites, and incorporation into the crystal structure. This results in a layer that's structurally continuous with the substrate, with minimal defects and excellent electrical properties. This epitaxial layer is critical for advanced CMOS, bipolar, and power devices, where junction depth, doping profiles, and defect control are paramount. Figure shows a typical diffusion furnace structure. We will briefly discuss the operation principle of a diffusion furnace. The diffusion furnace consists of a high-purity quartz tube that houses the quartz wafer boat, that carry the wafers to be diffusion. The dopant pre-deposition stage is a high-temperature process where a concentrated layer of dopant is introduced to the wafer's surface. The wafers are then subjected to the drive-in step. Surrounding this tube are multiple zone-resistive heating elements, each independently controlled to maintain precise thermal conditions. The furnace follows a carefully designed thermal profile, typically ranging between 1000 and 1100 plus or minus 1 to 2 degrees Celsius. Zone 1 ramps up the temperature and preheats wafer and prevent thermal shock to the wafers. Zone 3 is the ramp-down zone, wherein the gradual cooling prevents thermal stress on processed wafers. The Zone 2 has a steady temperature, diffusion zone, wherein the core doping process occurs. Carrier gases like nitrogen and oxygen are delivered via mass flow controllers, while exhaust systems scrub toxic byproducts to ensure safety and environmental compliance. Altogether, the diffusion furnace is a precision where thermal control, gas chemistry, and timing converge to shape the electrical characteristics of semiconductor devices. In semiconductor diffusion, dopant concentration distributes radially across the wafer surface. Hence, not suitable for shallow doping profiles. Ion implantation is a process used to dope a semiconductor wafer by bombarding it with a beam of energized dopant ions. Due to its superior control and precision, it has largely replaced diffusion. In ion implantation process, dopant atoms are first ionized and then accelerated using high-voltage electric fields to form a focused ion beam. This beam is directed onto the semiconductor wafer, allowing ion to penetrate the surface and embed at controlled depths. The dose and energy of the ions determine the concentration and junction depth. Ion bombardment causes crystal deformation and needs annealing to restore the structure. This method offers exceptional control over dopant profiles, making it ideal for shallow junctions and advanced device architectures. Physical vapor deposition is a vacuum-based process used to deposit thin films of material onto a substrate, typically during the metallization phase. The principle of operation is as explained below. The targeted solid material is placed inside a vacuum chamber. Using either thermal energy or ion bombardment, it is vaporized into atoms. These atoms travel through the vacuum and condense onto the substrate, forming a thin, uniform layer. There are two main PVD methods, thermal evaporation and sputtering. Thermal evaporation is ideal for high-purity metals like aluminum or gold, while sputtering, especially RF sputtering, is preferred for complex materials, including dielectrics and barrier layers. In MOSFET fabrication, PVD is used to deposit gate metals, interconnects, contact pads, and barrier layers. Post-deposition annealing is often required to restore crystal structure and reduce defects introduced during sputtering. Chemical vapor deposition, or CVD, is a fundamental technique used to deposit thin films in semiconductor manufacturing. Unlike PVD, which relies on physical transfer of atoms, CVD uses chemical reactions to form solid materials directly on the substrate surface. In a typical CVD process, gaseous precursors are introduced into a heated reaction chamber. These gases undergo chemical reactions, either thermal or plasma-assisted, resulting in the formation of a solid film and volatile byproducts. The solid material deposits on the substrate, while the byproducts are evacuated by the vacuum system. CVD is widely used to deposit dielectric layers like silicon dioxide and silicon nitride, as well as polysilicon, tungsten, and barrier films. It offers excellent conformality, making it ideal for coating high aspect ratio structures and complex geometries. In MOSFET fabrication, CVD is critical for gate dielectrics, spacer formation, and interlayer dielectrics. The structure of a thermal oxidation furnace can be either horizontal or vertical in configuration. The system consists of a high-purity quartz process tube that serves as the reaction chamber. It holds silicon wafers during oxidation and prevents contamination. The wafers are placed in quartz carriers and are loaded into a boat loader. This setup ensures uniform exposure to the oxidizing ambient across all wafers. The quartz tube is surrounded by heating zones, created by resistive heaters. These heaters are precisely controlled to maintain the high temperatures required for oxide growth, which typically ranges between 800 to 1200 degrees Celsius. The gas delivery system introduces the oxidizing agents. For dry oxidation, pure oxygen is supplied. For wet oxidation, water vapor is introduced. Some of the popular application of oxidation process are: dry oxidation is used to grow ultra-thin gate oxide, wet oxidation is used to grow thick field oxide. Following are key processes used to remove or trim specific layers during semiconductor fabrication. They are: wet etching, dry or plasma etching, ashing or plasma strip, chemical mechanical planarization, laser ablation or trimming, wet cleaning, etc. Let's now consider various processes used for removing or trimming process layers during semiconductor fabrication. These techniques are essential for patterning, cleaning, planarizing, and refining device structures at different stages of processing. We'll begin with wet etching. This is a chemical process where liquid etchants dissolve specific materials. It's isotropic, meaning it etches in all directions. Wet etching is simple, cost-effective, and highly selective between materials. However, it lacks precision and isn't ideal for features or advanced nodes. Next is dry etching, particularly reactive ion etching, or RIE. This method uses reactive plasma to remove material directionally, making it anisotropic. It offers excellent control over etch profiles and is widely used for trench and via formation. The trade-off is potential plasma-induced damage and the need for tight process control. Let's review the physical structure of a typical CMP system, that engineered for wafer-level precision planarization. The system consists of a rotating platform that supports the polishing pad. Above the pad, we have the carrier head, which holds the wafer face down and applies controlled pressure. Surrounding the wafer is a retaining ring, ensuring it stays cantered during polishing. A slurry delivery system dispenses a mixture of chemical agents and abrasive particles directly onto the pad. Now, let's explore CMP methodology, which is a hybrid process, combining chemical and mechanical operations. The chemical component of the slurry reacts with the wafer surface, softening the target material like oxide, metal, or silicon. Simultaneously, the mechanical component, abrasive particles in the slurry, physically remove the softened material through friction with the pad. The carrier head applies downward force, while the rotating pad ensures uniform material removal across the wafer. This results in creation of a planarized surface, which critical for subsequent lithography steps and multi-level interconnects. CMP is not just about removal, it's about precision leveling, defect control, and integration readiness. Metallization is the process of patterned metal layer deposition and create electrical pathways within integrated circuits. It enables connectivity between devices and logic blocks. Generates vias that connects between vertical metal layers. Contact pins of the transistor. The interconnects created realizes the desired electrical functionality. Metallization process consists of several processing steps like surface preparation, contact and via cut creation, photolithography, isolation layer and metal deposition, planarization, passivation layer deposition, etc. Some of the processing steps in metallization are shown in the figure. Thanks for your time. Hope this video has been helpful in getting an overview of key semiconductor device fabrication stages of crystal growing to the metallization. Thanking you once again and hope to meet you in the upcoming video. Bye for now.